All right. Okay, so let's start with our resistance equation. Problems. So let's start with, we didn't do anything on copper, so let's try copper. Obviously the only thing which changes the resistivity. So let's start with, so let's say I have copper and, let's take thickness, same 0.5 micron, and width is 0.1 micron, length is 10 micron. The same thing we kept for aluminum yesterday. So copper resistivity. So this is resistivity is, what was it? So I think 17 milliohms micrometer. So first thing, what is the sheet resistance? R sheet or R square? What is the sheet row? Yeah, this thing you should be able to do quick now, if you're following and have no questions. Okay, Sundarani says resistivity by height. Okay, good. So 34. Also give the units. Okay, so 17 milli. Always write the whole unit so that way you're not making any mistakes. By 0.5 micrometer. So micrometer cancels, and this is 34 milliohms, right? Good. And so now what's the total resistance from this end, the long end, this end to this end, total R. So this is sheet row. So this is 34 milliohms per, sorry, not milliohms, milliohms per square, right? So I asked you the sheet row. So per square of this 0.5 micron height is going to be 34 milliohms. And the total resistance is what? 34 milliohms by per square times number of squares, and the number of squares is 10 by 0.1, which is 100. So 3400 or 3.4 ohms, right? The total resistance. And if you remember in aluminum yesterday was, I think, 5. Yeah, I think 5.5 ohms because it was 27 milliohms millimeter. Okay, good. So so you can see, why people want copper. And for example, now if you have a tungsten via, right? We calculated tungsten via, what was the resistance we calculated? So this was 0.1 by 0.1, and it was 2 micrometer height. Okay, so what is this resistance of copper now in copper? What's the total resistance of this VI if it was in copper? Come on, guys, quick. What is it? At least I want one answer. 3.4 ohms. Okay, let's see. So 3.4, 3.4. So I guess it's got to be right. So 34 milliohm micrometer divided by the height, which is 0.1 micrometer, times L, which is, times L, which is 2 micrometer divided by 0.1. So that's what's 68 times 100, so 6.8 ohms. How come everyone got 3.4? Everyone agrees with this, or I made a mistake? Agreed. Okay. All right, so I think you guys all took 1 micron height. It's 2 micron, so that should be 6.8 ohms. So yesterday, remember, we connected metal one via metal one and tungsten via. We calculated the source to source end, right? So basically, we had a Pmos, right? And so this was one via the total wire resistance. So this was R via, R via, R wire, and then obviously the second via, and then you had the source of the Nmos, right? So this was for our inverter. So this total resistance was how much? This was, I think, roughly 11 ohms, if I remember right. 11, 5, 5.5. So yeah, so 20. So we had 11 ohms, about 5.5. So roughly, what is it? 22, 27, 28, let's say. So total was 28 ohms, right? This was with aluminum, right? AL. With copper now, what did we calculate? 6.8. So it's so with copper, it's 6.8 times 2 plus, what is the wire resistance we calculated? 3.4, right? So that's roughly 14, so like 17 ohms, roughly 17 something. So you can see there's a huge difference going from tungsten, aluminum to copper, right? So if you do both your vias and the wires in copper, your resistance improvement is, how much is this percentage wise? So you go from 28, so 28 minus 17 divided by 17, or divided by 28, I guess, if you're going from aluminum. So 40%, you have 40% improvement, which is huge, because getting a 40% improvement in transistor takes you like, 5 to 10 years worth of process development time. So so going from aluminum, tungsten to copper is huge. So that's why people want to go from the aluminum, tungsten to copper, right? Okay. Let's do some capacitance problems. Okay, any question on the previous one? Everyone agrees with it, or you have any issues with that? Okay, let's start with a simple parallel plate and air in between. Okay, and so what's the formula for this cap? So between these two caps, C equals to A times epsilon naught over D, right? So let's say this was the distance. Okay, now let's say if I fill this gap with SiO2, how much does the capacitance increase or decrease? Relative permittivity of SiO2 is, let's say, roughly 4. So you had C, how much, what is the multiplying factor to C now if I put SiO2 in between? 4C, correct. So this is 4C now, right? So you go 4 times. So this is, this is considered as high K because you're 4 times more than this thing. Now, for routing purposes, do you want high K or low K? Low K, right? Because you don't want routing capacitance, you don't want high parasitic capacitance. But if I was doing analog design, like I said, I want high capacitance, right? Then I need high K. So actually, people are doing process development on both sides. They're trying to do high K dielectrics for very niche analog kind of thing, and they're trying to do very low K SiO2s for very digital oriented chips, right? So that's how it is.
Sir,
Yes.
sir, I didn't get where we need high capacitance and where we need low capacitance.
Well, you saw yesterday, right? When we did this problem, right? This problem when we did it, we
Yes, sir.
did a capacitance calculation too.
Yes, sir.
Okay, so what does that capacitance do?
Sir, it is mainly parasitic type, so we like kind of avoid it, or we want it negligible, we can say.
Yes, we wanted, so you want low K or high K?
In this case, we need low.
Okay, so you got your answer there, right? So what's your
Yeah.
next question? Where do we want high K?
Yes.
So high K is, like I said, in analog circuits, like for example, you're doing an audio amplifier, right? If you're doing audio amplifier, you need audio filter. The filters are in kilohertz range. When the filters are in kilohertz range, let's say your resistances are 1 kilo ohm, then your capacitance needed are in pico to nanofarad. Okay, but if you have a low K dielectric, then the area needed is high, right? For a given capacitance, the area, because it A times epsilon over D. So if your epsilon is lower, then you need more. So your C is equal to epsilon naught A over D. So if your C is, um, I mean, if your epsilon is low, which means if you have a low K dielectric, that means you need a higher area to get the same amount of capacitance. This D is, let's say, fixed because that's your technology node parameter, right? Okay, so that's why in analog ones you don't want to spend a lot of area. Area is cost in any IC design. The more the area, the more the cost. It's just proportional. If your chip area goes from 1 millimeter square to 2 millimeter square, your cost of that die, silicon die, is going to double. Okay, and nobody wants that. So in analog, that's why they want high K dielectric. But obviously, it'll also increase your routing capacitance in analog. But so that's why, like I said, it's always a double-edged sword. But most of the research goes into doing low K because the biggest amount of semiconductor ICs are in the digital region. Okay, so looks like I made as in a previous question, 17 million by zero point 0.1 times 2. Oh, yes, yes, correct. Thanks, Samya, because I took this as 34. This was the million per square. This is a sheet row, but this I need as row, right? So this is row times height times L over W. So this should be 3.4. You're right. So this is even. Okay, so it looks like it's 3.4 for everything, right? So it's 3.4 times 3, which is for 3, 12, roughly about 13 ohms. So this is even better. So 13 is, it's more than 50% reduction basically. So yeah, so thanks Samir. That's correct. I took the sheet row. I should, because this is zero point 0.5 micrometer height, but you can see this is 0.1 here, the one I had taken. All right. Did that answer your question? I forgot who asked the question. Was it Sumant or um,
Right, so this.
Swadesh? Did I answer your
Yes,
question?
sir. Yes, sir.
Okay, good. All right. Now let's do some more. Capacitance are like your bread and butter in IC design. You should. Um, okay, so I take again the same distance and everything, and it's air or again or yeah, let it be air. Now I put a small sheet of metal. I cover this whole area with a sheet of metal, like thin sheet of metal. So previously it was this capacitance was C. What will be the new one? What is the new one C dash going to be with the new capacitor in between? Okay, quickly, guys. What's it? This shouldn't. I think you guys have done this problem. Um, so this cannot hear. Can you guys hear me? Can everyone hear me well or?
Yes, sir.
Okay. All right. So the question is, I take again a parallel plate capacitor like before, right? So it's some separation D. Let's say this was vacuum, so it's epsilon naught, and some area of A, right? So it gives you, and I put a metal plate in between the capacitor. What will be the new value of the capacitor? So it was C. Is it going to be 2C, 3C, 0.5C, 0.25C? Okay, somebody says C by 2. Okay, who else? 2C. Anyone else? C by 2. 2C. C by 2. 2C. 2C. Okay, so like the popular one seems to be like 2C. Well, all of them are wrong. I'll show you two ways. I'll show you the circuit ways and I'll show you the physics way. So this, you can model it as, okay, once I say it's wrong, we'll start correcting it. I can model it as two series caps, right? So this is two series caps. Now, because this one you can consider this is that metal node, right? Because it's a short, just thin metal. So that's your thin metal here. So what's this cap here? Because your distance is half, so this is 2C, right? This distance is half, so this is 2C. So if you have two capacitors of 2C in series, what is it? It's C, right? 3 by 2. No, it's not 3 by 2. It's still C. It's a thin sheet. Okay, now let me show you from the physics point of view. So you have, I'll just exaggerate it now though. So I'll take the separation like really far away. So, and then I put this in the middle, right? And I'll make the metal a little bit thick. Okay, so you know how we did it yesterday, right? We put positive charges here, positive charges, negative, same amount of negative charges here. And without this, the electric field went just straight to here, right? To the negative plate for each of these positive charges. But because I have a metal, so you cannot have an electric field inside a metal, right? Because there are free carriers, there will be a current flowing through it, but there's no connection to this. So there cannot be a current flowing through this. So you'll get electric field. Because I have free carriers, one negative electron will get attracted here. That'll result in a positive here, and that electric field will go and end in this, right? So it'll all be like that. Now, it is the same number of electric fields like before, and the electric fields are traveling the same, almost same distance, because I said this distance, this D is equal to 0, like it's a thin sheet, right? Which means that the potential is the same. If the electric field is the same value and same distance, because E is equal to V over D, so this is the same, D is the same, that means the V is going to be the same, the charge is the same, so C is equal to Q over V, right? So V is the same, charge is the same, that means the C should be the same. Okay, everyone agrees with this, or anyone disagrees with it? Okay, all right, so now you have the same distance D, right, like before. Now I make a thick metal, like this. Let's say that the metal thickness now is D by 2. This, so I put a thicker metal now. What is the new C dash right now? And by the way, I'm not making these problems up. These are real IC problems. So in routing, this is how you calculate capacitances. So you'll have like intersync capacitances and this thing. Okay, 2C, anybody else? 2C, 2C, 2C. Yeah, I think this one, everyone gets it correct now. So that's because this is now D by 4, right? So this is D by 4. There's no electric field inside this. So if I had to model as two capacitors, this will be 2 again in series. This is 4C, this is 4C, and the total is 2C, right? And same thing, you can use the you should always look at it from the electrical field analogy, because that's when, if you get confused, that's the only way to get out of your confusion. If you have the picture, the field picture, then because capacitance is very easy to get confused, especially when you start doing series and charge capacitance and all that. It's very easy to get confused, especially series ones. So here, same thing, you get the same charge. So now it is the same value of the electric field, right? Because you have the same amount of charge, but they're traveling only half the distance, because there is no electric field inside a metal. You cannot have electric field inside a metal because there are free charges, right? So you cannot have electric field metal in it. So um, so if it is traveling half of it, then this V will be also half of it, right? It's electric field is V over D. If the electric field is half, then the V is half, because the distance, the distance is half. So V is half. V is twice, sorry, V is twice. So that means, so electric field is the same. Now distance is D by 2. Sorry, electric field, yeah, V is half of what it was before, right? Because for the same charge now, the potential is half of it. And then that means the C is basically, C dash is twice of that. Okay, so you can look at from a circuit point of view or the physics point of view, field picture, it should give you the same answer. So, okay, everyone got this one right. Okay, now I take the same plate again, distance. And in vacuum, this was again C. So it is some area and distance D again. Now I fill it with silicon, crystalline silicon. Okay, crystalline silicon. What's the new C dash? First of all, is it a capacitance or is it a conductor? What is it? And if you want to, you can leave a thin gap here if you say no, it's going to conduct. So what's C dash here? Okay, 0. 0. Anybody else? Is there any thin layer between metal and it doesn't matter? But okay, so if you're getting confused, so let's say I put a thin, so instead of doing this, I'll just give a little gap. Gap like this. So I fill with crystalline silicon. Now what is the capacitance? Okay, so people are saying 0 because you have a material in between. Let's say there is no conduction. Let's assume there is no, because you remember the carrier in an intrinsic one was very, very low, right? The electron concentration was very, very low, we saw yesterday, which means that if I put electric field, then there's not going to be conduction. If there's no conduction, then the electric field will just go through it. But the electric field is going through the material. It's not going through vacuum, right? It's still going through SI. So if that's the case, then all I need to know is what's the relative dielectric constant of that silicon. And silicon dielectric constant is what? About 11.7, which is about 12, right? So whatever the capacitance was before, that will be now 12C. Okay, Sumant, you have a doubt. Go ahead. What's the question?
Sir, in the first case, you said that the capacitance will be C while calculating. So,
Yeah.
what is the need of the dielectric medium in between if it remains the same?
Where? Which question are you asking?
Before to before question, where we got the C dash equal to C.
You're talking about this one? with a
Yes,
thin
sir.
sheet in between?
Yes, sir.
What is the need? No, no, no. I'm just asking you, if I put a metal, then what is the C? That's physically possible, right? Because there could be another routing cap here.
Okay, sir.
Okay. Or it could be a sheet charge, right? Like we calculated yesterday for the inversion layer. Inversion layers are thin sheet charge. They don't have a thickness. The thickness is like few nanometers and they look like a sheet charge. So that's what I'm asking you. If I put a sheet charge in between, what happens to the capacitor in between? So I'm asking you as a problem. You're asking me if it is C, why am I doing it? No, I'm saying physically this is what happens in a lot of cases. Then what happens to the C? Okay.
Okay, sir.
Okay. Got it, right? All right.
Yes, sir.
So everyone clear about this one? Why is it 12C and why it is not 0? See, if it is 0, there will be no electric field going through it. It has to go like infinitely somewhere else, right? Because I put some charge here, right? That charge has to end somewhere. If it is going like this, so that is the distance you have to calculate it. So it can be 0 because I have negative charges here. So even if there is only fringe fields here, there will be some cap, right? You cannot have 0. But actually the field will go through straight through the silicon because it is a crystalline material. You can pass it's not metal, right? So if it is not metal, then electric field will go through it. If it was a metal, then the electric field cannot go through it. Okay, so everyone clear about this one? Okay, now what if I so let me change this problem a little bit. So I have same two parallel plates and air in between. So capacitor is C and this is D. Now I do take a P plus silicon, heavily doped P plus silicon, and this is, let's say, D by 2, and I insert it in between. There is no connection. The connection is only from here to here. So this is V, this is ground basically. Okay, there is no connection here. It's a slab of material. So this is your plate, this is your silicon, that, and that's your plate too. Okay, so what's this C dash right now? So this is a, like I said, it's a heavily doped P plus silicon. What do you think will be the capacitance? Conduction will be 0, so cap is 0. So for this, when conduction is 0, cap is not 0, right? When conduction is there, then the cap is 0. Unless the electric field is just emanating somewhere in, in the moon or someplace, right? Okay, Soumya says 4C. So why, Soumya? Why is it 4C? Anybody else? Abhinav says 2C. Okay, so this is 2C. Okay, Abhinav, can you come online and explain why is it 2C? So 2C is correct. I want to know why, how you came to that answer.
Hello, sir. Am I audible?
Yes, yes, you're audible. Go ahead.
Sir, like we calculate capacitance for a MOS, so the P as P plus is heavily doped, so it will act as another terminal, and as its length is D by 2, so the upper remaining length will be D by 4, and the lower length will be D by 4. So
Okay.
the equivalent capacitance will be 4C series 4C, so it will be
Yeah.
2C.
Good. But then why is there no electric field inside? So okay. So let me draw what you just said. So you said all electric fields will come here. So that's, since I've drawn D by 2, so this is D by 4, right? This is D by 4. Then you have D by 4 here. So this is, so d by 4, this is 4C, this is 4C, and then this is equivalent to C. Why is there no electric field in between, inside the P plus like we had here? Is that what you're assuming, right?
Yes, sir.
Why is that? This is what you're assuming basically. And my question is, why is that? This is correct, but I just want to know if you understood
The
it correct.
conduction will be inside the P plus.
Well, first of all, you have to realize that this is a floating material. There cannot be any conduction, right? DC. So we're talking about DC here, right? Obviously, if you do AC, that's a whole different thing, but this is DC. Someone says it will neutralize in its own. I don't know what that means.
Like those dipole case.
Yeah, kind of, not exactly dipole. So this actually looks like a metal, right? Because you see, in this case, you didn't have any carriers to conduct, right? So you cannot have conduction. If you have carriers in conduction, so for example, a metal, you put electric field here, they will just terminate right here because there are carriers. You cannot have electric field inside this, because if there are electric field inside this, because they're free carrier, they need to keep continuing flowing, but they need to conduct, right? So if the metal is just standing in free air, there is no path for current flow, then there cannot be any electrical field inside it, right? Same thing with P plus, but in case of a silicon or a dioxide, you can have electric field going through it because there is no conduction. There is no free carriers inside it, okay? So that's why in a P plus, so what will happen is you get electric field here, right? What is the majority carrier in P plus? Holes, right? So this electric field will drive away the holes because they're free carriers and leave a negative charge, which is a immobile charge behind. And the positive end will go here to this place, and that will start the electric field from here to here. There cannot be any electric field inside this. Okay. And this is obviously the depletion region, but since it is P plus, if you want to be really accurate, then you want to take the depletion capacitance as well, like what we calculated, but this is very thin. So that's why you don't worry about the depletion. Did that make sense? So yeah, 2C is correct. Does everyone agree with it, or you don't understand some part of this? So P plus, heavily doped P plus looks like a metal basically. Okay. So if it is like a metal, then obviously you're going to get free carriers on both sides. And obviously it's not free carriers on both sides. The big difference between the metal and this thing is that you actually get almost a free carrier on one side and negative on the other side. Here it's a mobile carrier because it's in a lattice, whereas in a metal, it's actually a lattice there too, but it's the mobility is much higher compared to P plus. Okay, clear? Okay, so I'll ask the last question, which is related to the MOS. So when we do the MOS capacitance, this will be more clear. So you have a plate like we had before, right? You have another metal plate here. But now I'm going to put a lightly doped P minus, but I'll actually connect the metal to the P minus. So this is metal, right? So let's say this is aluminum. This is P minus in the sense that lightly doped, what do you call it? Silicon. So this is silicon. And then I put, let's say I fill this with silicon dioxide, SiO2. And so this is a metal plate, obviously, and this whole thing is silicon, this whole thing, I mean, silicon dioxide. So that's your structure. Now, what's the capacitance? So this is some A. So what's the total capacitance from this node? So let's call this node G, let's call this node S. So what's the total capacitance CGS, just the way I have shown it here?
So the distance between.
Yeah, so let's take some distance. So this is, let me call this Tox. Let me call this TSI, let's say. Okay, thickness of this thing. And so let me do this then. I'll give you the unit area capacitance between this terminal and let's say I had a sheet of charge here. That I'll tell you that that's Cox. You just take it for granted. So in other words, if I had a metal here, then the unit area capacitance will be Cox, and total capacitance will be Cox times A. Okay. So just express it in terms of Cox and whatever. So let's say this capacitance Si was CSI per unit area, or whatever it is. Just tell me what will be the total capacitance. First of all, does this remind you of any structure we discussed yesterday? Anyone kind of does this structure look familiar to you from yesterday's? Okay, Praveen, what does it look like? Mass, yeah, exactly. So so this is metal, this is your oxide, this is your semiconductor. Obviously, this is a metal just to connect the SI. Now, if you connect a metal just to SI, it'll form a Schottky contact, but just forget about it. So assume that this is a ohmic contact. And so this is a metal oxide semiconductor. And do you remember what happens if I put a voltage? So if I put a positive voltage V here with respect to this node S, what happens? You'll have positive charges come here. And because this is silicon dioxide, so obviously the electric fields will go and they'll start kicking away some of the, because the majority carrier is holes, they'll kick away some of the holes. But now because there is a path to your battery terminal, the holes will just go away and get eaten away by this battery basically. So you're putting a battery across, right? So whatever charge you're coming here, it'll just flow through the circuit and come back here, right? So you have a circuit to complete now. Now, because I said P minus, this layer is not going to be very thin. So it's going to be, right? So it is going to be like this. Now, what should be the capacitor? Now, what should be the capacitance from G to S now, knowing this? Cox times A, okay. Now, if it is Cox times A, all the charges should be right here. Okay, so let's say this distance was XP. We calculated this distance, right? So there is this. So if it is Cox times A, then all your negative charges should stay right here in the edge. And this is what happened when the channel turns on. If you remember, after we go to VT, that's when it happens. I'm saying channel is not turned on right now. So there's just a depletion, right? There is a depletion. So what will be the cap? So you remember we calculated reverse bias diode. So if you had a PN junction, and you did a reverse bias like this, you remember this depletion actually was a capacitance, right? Cj equals to Cj naught divided by 1 over square root of 1 plus, I think, what was the capacitance value? 1 plus VR should be Cj naught feed to, yeah, feed to, no, not feed to, because when VR is equal to 0, it should be Cj naught. So 1 plus, 1 plus VR. And when VR is high, capacitance should be low. Yeah, VR by phi naught, right? So that was your expression. So you actually have a capacitance between this node and this node, right? And that's your depletion capacitance. So what you actually have is Cox in parallel with Cj, and that's your total capacitance. So it's a series capacitance of C. So the total capacitance is going to be Cox times Cox plus Cj. Now this Cj is actually much lower compared to Cox most of the time. Okay, which means that this total one will be very close to Cj, which is a small cap. So when the channel is not turned on, the gate to substrate cap is actually a very small cap. And this you will see when we talk about MOS caps, why it is important. So when you switch it off, you have a very low capacitance. And this is something people get confused. They actually still write CGS, and it's not CGS. It's actually COX in parallel with CJ. Maybe it'll be a little bit more clear when we start doing MOS, but at least did this make sense? So if I put a P plus material here, like a heavily doped P plus, then it will be very close to COX because the doping is so heavy that all your charges actually are on the sheet. So then it looks almost like COX. Okay, but because this is lightly doped, you're going to have a kind of a fairly large distance between them. Okay, makes sense. Any questions? Okay, good. This was a good review. I think it looks like a lot of you are following what's going on. All right. If you don't have any questions, so what I'll do is now we'll go to the second part of the MOS equation. And but before I do that, let me just quickly 5 minutes. I will go through the threshold part of it, so that way you'll have some continuation. Okay, so let me just quickly go through this, and then if you have any questions, we can talk about it. So before we went for the 4-terminal devices, like I said yesterday, we went with just the MOS structure, just to calculate the threshold voltage. What are the parameters responsible for turning the channel on and off? Because that's essentially what we're trying to do. We're trying to create this 3-terminal device, which we can control the resistance between 2 terminals by controlling the voltage on the 3rd terminal, which in our case in MOS is a capacitive one, which is sort of ideal for low power application. That's the whole idea how people move from BJT to MOS, is because in MOS you always have a base current. Here you don't have that DC base current. Actually, people were trying to always invent MOS right from the beginning. The BJT actually was accidentally discovered while they were trying to discover MOS. So if you look at the history, it's pretty interesting. Okay, so we looked at the MOS structure where you have a metal in IC design. That metal is polysilicon, and if you apply a voltage across it, then like I just showed, you're going to have electric field across the oxide, ending in the P type, which will drive the holes away because that's your majority carrier, and it'll leave some immobile charge at the interface. And now, since this is usually a lowly doped, it's not going to be very thin. It's going to be, have some distance, like as we said right now. For some reason, I'm not able to see the chat. 1 second, just give me a second here. Oh, Ashwini says not audible. Can you guys hear me?
Yes.
Okay, so Ashwin, it's on your side.
Yes, sir. Yes.
Yeah. Okay, somebody asks, is BJT still used? Yes, of course, BJT is still used. There are different type of BJTs like IGBTs and so on. So wherever you need like a really large amount of current and high power, that's where, and high speed as well. So BJT still outperform MOS's. So like I was telling you, your power amplifier, right? So power amplifiers are actually, a lot of them are. So the BJTs are different from, like in gallium arsenide or HAMT, they're kind of BJT structures, but they are band gap engineered. But yeah, they're definitely used. And so you have. So by the way. Maybe at some point we'll cover that. Even in a CMOS process, you get what's called parasitic BJTs. So you always get NPN, PNP structures, like the band gap we do for voltage reference, constant voltage reference. In those we use BJTs. They are not very good BJTs, but they're good for voltage references. So there are a lot of bi CMOS processes. So bi is basically says, it's a BJT plus CMOS. So the process is such that you can have high quality BJTs and this thing. Yeah. So Abhinav says, yes, sir, latch up, we get BJTs. Yeah, exactly. So you get latch up because you get two BJTs back to back connected with a huge base resistance. So you get latch up in CMOS. We'll talk about latch up. We'll cover some of the advanced topics after we finish the inverter characteristics. So we'll go into detail some of the this ancillary CMOS stuff. But short answer is yes, BJT is used, still used, and there are a lot of still applications. So the CMOS is primarily driven by the digital. Obviously, there's still a lot of analog also. 99% of the analog, probably not 99. I don't know actually what it is, but a heavy amount of analog is still CMOS, but still a lot of BJTs. But all digital is purely CMOS. You don't get BJTs in digital. Okay. All right. So. So we looked at this and we said, once we applied a voltage, you get electric field. That electric field doesn't end on the oxide side because you have a p-type. So it kind of flows through in and drives the holes away, creates the depletion region, and you keep increasing that depletion region increases. And the voltage, which is most important for the threshold voltage, is the voltage at the interface, which we call the surface potential. So that surface potential is also increasing. And when it reaches a value 2πf, which is 2 times the Fermi potential of the p-type material, then a channel is formed there. And this channel is a n-type channel. So that's why it's called inversion, because it inverts the p-type to n-type. Okay. And at this point, whatever is that gate voltage, we call that gate voltage as the threshold voltage of this device, right? And so now, we go about calculating this. So we use KVL around the loop and say, okay, this gate voltage is the oxide voltage plus whatever is the voltage across the depletion range, which we call it as the surface potential. And this is, like I said, we define this as your threshold voltage, which in this case, this is a Nmos we are trying to build. So we call it VTN. And this voltage Vox is basically whatever is the gap plus, divided by the Cox. Not exactly right, because there is, like I said, there's a distance XP in it, but this is a smaller portion compared to the rest of the voltages, so it's still pretty accurate. And this value of the Q dep, we went into detail how we calculated this yesterday. So we just plug that in, and that gives you what's called the VTN ideal, right? And then we looked at what's called the contact potential, and I think a lot of people still have questions about it. Like I said, it's not very intuitive, it's counterintuitive, but take a look. Civitas, like I said, probably has one of the best explanations. So look in that text if you want. But essentially, it tells you the potential which is formed. It's like built-in potential, but what you see when you have contacts on both sides. But when you have the contact, you can measure them. Like as I said yesterday, if you put a contact, this is metal, and phi m1 minus phi m1 cancels out. So you don't see that, but it's the potential you see prior to the contact, basically. So I'll just skip this. And yeah, so the key factor is if you have a stack of material, doesn't matter what material in between, the contact potential is the work function difference between the two materials at the very end, 2n. So in this case, it's m1 minus mn. Okay. So, like I was saying, if you have oxide, semiconductor oxide, it's still M1 minus Mn. If you have silicon, metal, blah, 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 it's still M1 minus M1. So that's the key thing to grab from here. So that's the correction we make. And this value is usually called the flat band voltage. And, like as I showed, in the band diagram, it tells you why it's flat band voltage, because the band bending which was done at equilibrium, now you add an electric field to make that band bending flat. So that's why it's called a flat band voltage. And you can calculate this value, and you can see this equation is pretty much same as is your built-in voltage for your PN junction, right? So, And then see if you make that correction to the last equation, so you add that flat band voltage plus the QB over Cox plus 2Vf, and that's your new expression. We took an example, and this is Cox value. I think this is for 0.18 and a certain concentration, typical concentration of your p-type and your poly. And if you plug that in the equation, it turns out to be minus 0.25. But since we are trying to make a Nmos, we want this to be positive. So this is called a depletion mode device. So if you don't do any engineering at the surface, then this device is what is called a depletion device, and we can, and they are useful. So depletion mode, actually use them for MOS capacitors, because this MOS capacitor is much higher density than your other capacitor between poly, metal, and all that. So in analog design, specifically, we use this MOS cap a lot. Okay, and so having a depletion mode, then you don't have to apply a voltage before it becomes a cap. You can just start using it at even at 0 volts. So depletion mode devices are still very useful in IC design. So we looked at how to create enhancement devices where the VTN is greater than 0 volt. So like I said, we artificially implant ions, basically negative ions, so that we have to apply a positive voltage to first overcome this negative ions. And these are immobile ones, because you can't have mobile charges here, because then the channel will be conducting all the time. So you do immobile ion implants here, just like you do for your N plus, P plus, and so on. Actually, I'm sorry, not like your N plus, because in N plus and P plus they are mobile, but you do implants which are unlike N plus, P plus, where they're not mobile. And you do that, and if you have a certain, and these are done at very thin layer just at the surface, so usually they are presented as ions per unit area, because you just don't have any depth. And even if you did, you just take that depth into the picture like we did for our sheet rows and all that. So you add that in. So Q times di over Cox is the voltage now you need to apply to overcome this. So you can call this as like your VDI, so your implant. And in your if you take the previous case now, and like I just said before, this is, I've given you a DI and I'm telling you what it is, but people usually go the reverse, right? So they say, oh, I want this is 0.18 micron technology. I want at least 0.678 volt threshold voltage. So if it is 0.678, then you want this voltage, QDI over Cox, you want it to be 0.98. So Q, that's a physical parameter, Cox because that's given for a technology. Then you calculate DI based on that, which, in this case turns out to be 2 times 10 to the power 12 ions per centimeter square. And you do that kind of bombardment, then now you are going to get your positive VT voltage. Okay. And so now we make that correction. Plus, like I said, when these things are fabricated, since the silicon dioxide is going through a lot of this gaseous process, growing over an interface and all that, there are a lot of impurities, mostly at the interface between silicon and oxide, as well as inside as well, because these are usually grown layer by layer. So if there is an impurity in the gas chamber or anything like that, that impurity gets trapped. In fact, those are the biggest difference between expensive fabs and cheap fabs, right? So you have cheap fabrication houses where they're cheap for a reason, right? Because their quality of their equipments are not that good. So when you get devices, the devices are also cheap. It's like they say, you get what you pay for. So for example, you go to TSMC, IBM, and all these places, they are like really the highest quality fabs in the world. So there, the impurities are going to be really low. And like I said in the beginning, in the enhancement, if you had a depletion mode device, your cap is going to just look like a parallel plate cap, right? So it is going to look like this, and this will be Cox times W over L, whatever is the area of your gate. In this, so this should be what it would be for your depletion mode. It looks like a normal capacitor basically, and like I said, we use this a lot in analog IC design, because this Cox, it's much larger than C metal, silicon dioxide and so on, because the thin ox is about 27 nanometer, like whereas in a 0.18 now it's like 4 or 5 nanometers, right? Whereas yesterday we were calculating this, the distance is like 180 nanometers, so you get orders of magnitude improvement in your COX by using the MOS thin oxide. But then the downside is your breakdown voltage is also lower, right? So if you're using a MOS cap in 1.8 volts, then your breakdown is 2 volts. You can't go higher than 2 volts, which is fine because most of the time you're using it inside your transistors, which has to be limited to 2 volts or 1.8 volts anyways. But if you have so this is your enhancement mode transistor, and you can see till you get to VT, there is no charge, or the charge is minimal, and then after that it looks like your COX basically. COX times W over L. So if you want to calculate the charge accumulated on the gate, then it's COX times W times L, that's the total capacitance, and then it's the excess voltage, right? Because till VG equals to VT, you don't get anything. So anything less than VG less than VT, this is a negative term, but there's no negative charge. Actually, there is accumulation charge. I'll show you when we get to the capacitance. But as you go excess of VG, so let's say for example, your VT was 0.5 volts. So till 0.5 volts, you're not getting any charge. Above 0.5 volt, let's say you give 1 volt, then your charge, your charge QI will be COX times W times L times 0.5 when VG is equal to 1 volt and VT 0 equals to 0.5 volts, right? So that's what's called the excess voltage. So I showed it in another way where I said, once the oxide is like the example we took, in that case, actually the charge is already formed. So what you do is you make it flat by applying a negative voltage first. You take it away, and then you apply 2Vf plus the Vox, which is the surface potential needed to invert the channel, plus the oxide depletion charge divided by the COX, which is the voltage needed to accumulate the depletion mode. Once you get to this voltage, then again you get charge inversion, and this is by definition the threshold voltage. And plus you have some impurities, you have to overcome that as well, positive or negative depending on what kind of impurities it is. And that's the definition of VT. I quickly showed you the band diagram also. So when you draw the band diagram, so actually just to be clear, so band diagram, so this direction is basically this direction here, right? So you're going from metal to oxide to, you're going metal to oxide to semiconductor. So metal to oxide to semiconductor. So that's the band diagram. So you can see that when you connect them together, because the law of thermodynamics says that your Fermi level should be constant, then because of that, this will bend by whatever is your work function difference between this and this. So your flat band voltage is basically applying that voltage so that this becomes flat. And when you do that, then the Fermi levels get separated by that voltage, Q times FB of that voltage. And then you apply the voltage to take care of the depletion, and then you apply the voltage to make the surface potential equal to minus Vf, such that the total is 2 Vf, and that's the inversion. And I was explaining yesterday is that if you look at the slice here, it looks like N-type. Now, in order for it to look N-type, this V has to be exactly in the opposite direction by the same amount than it was in the P. And that's why you get this 2 Vf, because it's Vf in this direction, which is given to you. You have to first bend it by Vf, another Vf to get it close to N-type. And that's why you need that surface potential to be 2 Vf. Once you do that, you get the inversion, right? And then I quickly showed you that this was, so obviously after you have the channel, you can add a N plus region on both sides, because the N plus regions have, majority carriers electrons, and then you can have a conduction channel. And that's the whole idea. You're trying to conduct between these two nodes, and the control terminal is this gate, because you're trying to create a voltage control switch for your digital circuits. But then I showed you that the source and drains are all not always grounded, because then Most of the time, the source is grounded, the drain is whatever the voltage. But like as I showed yesterday, if you have series devices like in a NAND gate, this source is some voltage. So when this source voltage changes to some, let's say VSB, then your depletion sort of the area increases, and that actually increases your VT, because the way to look at it is, I mean, it is kind of counterintuitive, because you might say, oh, it increased, that means I should reduce the voltage to bring it back to the original one. But no, because this increase, it actually changed the surface potential, because you didn't increase it by increasing the gate voltage, you increased it by increasing the source voltage. So what you need to do now is you basically pretend like, oh, what would be the gate voltage needed if the source voltage was 0? What would I need the gate voltage for it to have these extra depletion charges? And that's that extra voltage you need in the VT side. It's a approximation, but it's a pretty good approximation. That's why when we talk about MOS modeling tomorrow, we'll see that level 1 they use this, but when you get to level 2, 3, and all the complicated vSIM4 models, then it starts changing. Okay. And we derive the equations for this because we already have derived the equation how much charge is needed for a given voltage. So we use that equation to use it here. Obviously, all that is assuming it's homogeneous, purely square, and all that. You can see these are all very regular shapes. But like as I said, this is just level 1 for doing hand calculation. This is pretty good, but the complicated models take care of all the second order, third order, and fourth order effects and give you a more accurate results. So the idea is these equations help you to design, right? And then you use the SPICE simulator to analyze, to make sure that whatever you design is what you're getting. But what I see most people do is they use SPICE simulator to design. You don't want to use SPICE simulator to design, then there's a derogatory term in IC design, we call it spice monkeys. So you don't want to become a spice monkey who's just like pressing buttons and trying to get some results. So these level 1 models are still very good, because they'll get you very close to the accurate result, and then you use the simulator and tweak whatever you need to do it. And not only that, if you have any problems or issues, if you don't have a deeper understanding of what you're doing, then you would be just pressing buttons again in the simulator trying to get it working. Okay, so that's all I had for the threshold. Any questions before we won't go into the IV characteristics? Okay, so we'll proceed to the next part. So now that we have formed the channel, we want to see what is the relation between the current between the terminals. Now, because it is 3 terminals, we'll basically get sort of 3 sorts of equations. I mean, 2 sets of equation. One is what is the current with respect to the gate, and then what is the current with respect to the drain itself. And then the third thing we'll talk about is all the parasitic and the intrinsic capacitance in a MOS device, which are very, very important for high speed, high performance designs. Okay, so before I start deriving, and this is something I did, so that's why I did it. I didn't want to change it to a resistor, so that way it's familiar. So like I said, you can, the equation or the derivation we did for resistive material, it's the same thing applied for a sheet of charge or a doped semiconductor, because they have the free carrier just like everyone else, just that instead of resistivity, we talk about mobility in semiconductors. Okay. So, I explained yesterday, so I said we're going to derive the equation for a block of resistive material, And I gave you the reasoning, like circuit reasoning, that the field inside is constant because your voltage is linearly kind of dropping. And I showed you from a circuit perspective that these let's say this entire resistance was R. Then if I, for example, divide them into series R's of equal values, then all equidistance points, you get the same delta voltages, which means that it's linearly decreasing, which means that the electric field is constant among them. If you have electric field and you have free carriers, you're going to get a force which is going to make those electron or holes move, but they're not going to accelerate and keep increasing the velocity forever. And I was giving an example yesterday. It's like terminal velocity, right? A skydiver dives out, he starts accelerating at g, but then obviously the friction of the air starts increasing. At one point, the frictional force and g's are the same. So, and that's the terminal velocity. So in the semiconductor analogy, that terminal velocity is basically this Vd here, because you have a certain mobility, because the electrons are kind of banging around depending on the lattice and type of material. You get what's called the mobility of the electrons or the holes. In case of a p-type material, it will be the mobility of the holes. So that average velocity of the electrons passing through a certain cross-section area is proportional to the electric field, applied electric field. And when we look at short channels later on in the course, we'll see that as the electric field gets higher and higher and higher, it's not proportional anymore. It gets saturated at point, and that's the big difference. What we are learning is right now the equations we are deriving is what's called the long channel equations. And when you say long channel, you're talking about like 0.35 micron types of numbers. When you start going below 0.25 micron, 250 nanometer, you start getting these high field events, and so these equations need to be modified for that. So but they get really complicated since you are getting introduced, so we just keep it long channel to keep the confusion away. Once you get acquainted and get familiar with it, we'll introduce some of the short channel stuff. And even so, like for example, in analog design, I don't do designs in 14 nanometer and all that. They're usually 90 and 130 nanometers, but we still use long channel to hand calculation, and then you just do simulation. And in analog, most of the time you're using long channels anyway, and so your equations are valid anyway. It's only when you get to digital they use the shortest channel possible. But in that case, you don't have to be super accurate. You can be accurate to like 80-90% and then use the simulator to verify your design. So we said, the average current is going to be, the charge. Basically, we take a slice here, and we know that the current flowing through this is the average charge flowing through this per unit time. And we kind of separated the variables because we don't know what the average charge per unit time is. That's what we're trying to verify. So we separated the variables, and we said, okay, we can derive charge per unit distance, and then the velocity of the electron, and that if you combine it, then you'll get the current. So and we talked, like I said, in IC design, we don't have control on the vertical directions. We just control the X and Y. So we talk in sheet charge. So here also we talk about sheet charge, which is basically your volume charge divided by the height, how we have been calculating our resistances. And times W times Vd gives you that. So basically it's this equation here, which I've substituted the appropriate values. And then you plug in your, and QS is essentially related to your doping concentration, and WL and the height. And so what you get is finally V is proportional to I, and the proportionality factor has this process factor, which is the surface charge density 1 divided by surface charge density times the mobility of the electron or the holes, and then the geometry, and the geometry part is L over W. So so your resistance is basically this term here, which is process. This is the designer. So you, as a designer, you can change your L and W to get certain resistance. Or in case of like wire resistance, you're not trying to design this, you're trying to just get whatever minimum wire width you have and the length you need, and you just end up with this resistance. Okay, so as an analog designer, we use some material to actually create resistance, so we control the LW. In case of routing, it's just a parasitic element you get. Okay, now let's use all the previous um, derivations we have done. Now we'll slowly start deriving the IV characteristics for MOS transistors. And we'll look at it a few cases just to kind of give you an idea for different regions of operations, because this is not a linear element right now, it's a nonlinear element. So since it's a nonlinear element, that means the operation depends on the sets of voltages on this terminal. If it is a linear element, then we just do one equation, we're done, right? Because it's nonlinear, we're going to have different regions of operation depending on the voltages which is applied. So first, let's look at this case. So the case is, so we went into detailed derivation saying that, so this is your MOS structure, right? So this is your metal oxide semiconductor structure. And we said, if this gate to substrate, which is the same voltage as this source here, is greater than some value VT, you have this channel formed, right? You get this channel. And let's assume right now that the drain and the source voltages are pretty much the same. And you apply a tiny amount of voltage to the drain side. So if that's tiny, then we'll assume that this charge density actually remains same throughout the channel, right? So it's not varying throughout the channel. And if that's the case, we can use the previous derivation we did, because you remember the previous derivation we did, we said it could be a resistor, it could be a charge sheet, it could be a semiconductor block of semiconductors. So we'll assume this sheet of charge as our element which we just derived. So I just exaggerated this sheet of charge into this length W, which is the W and L of your transistor. And you remember from our MOS cap, which we just reviewed it, that the charge on this is going to be Cox times, and this is unit area, per unit area. So we're just talking about per unit area right now. So Cox times VGS minus VT, right? So the charge is whatever is the excess voltage above the threshold voltage times the oxide capacitance. That's the amount of charge you're going to have. This is NMOS, so you're going to have this positive charges here, right? So that's the charge. So that's your sheet charge. So, and then we just use the equation before, right? So IDS is equal to 1 over R. So IDS is equal to VDS over R. And you remember R, this equation, we said it's 1 over QS mu N times times L over W, right? So this is, because this is 1 over R, I just take the reciprocal of that. And so basically this is 1 over R, right? And so that's your equation there. And QS, we know that Cox times VGS minus VT. So that's your first equation. So, so for this condition, like I said, if it's a nonlinear element, so this is the condition. If your VGS is greater than VT and your VDS is very small, how small? Well, this is an approximation. It's a linear approximation. So you always have error. So it depends on how much error you can tolerate. So for example, if you are working on a 1.8 volt device and your VDS is 0.1 volt, you can use this equation to great accuracy, right? Because it's always inaccurate, it's always nonlinear. It depends on how much accurate you want. If you want like 0.01% accuracy, then obviously this is still not valid. You have to use the equation we're going to derive right now. But if you want like 10% accurate, obviously this is plenty good. And in fact, we use this as in analog design, we use this as a voltage control resistor. So VC as a voltage control linear resistor. So like, for example, yesterday people were saying, oh, can we design low pass filters? Yes, you can design low pass filters and high pass filters in analog, for example. So like this is a, high high pass filter, and let's say I want to change the corner of this high pass filter, I put a MOS device here in linear mode, and I control this gate voltage, then I can control the corner of the bandwidth of the filter. Okay, so we do use this as a linear resistor in case of in analog design actually. Okay, so that's the first condition. So if VGS is greater than VT, VDS is really small, you can just use this linear equation here. And it is, it's still voltage dependent, but for a given VGS, it's a linear resistor. So if your VGS is fixed at some VGS 0, then this voltage is fixed. W over L is obviously fixed. This is a process parameter. So your drain to source current is proportional to VDS by this constant here. Okay, now we are going to increase the VDS further. So now we can't make that approximation that the sheet charge is constant. Now we increase the VDS. Now you can imagine that because I have the source and the drain, right? And this is ground, and this is some voltage VDS with respect to your bulk. Now you can imagine. So if I slice these, right? So we did MOS device, and we figured out what the VTN voltage is. If I kind of slice this, right, and take one slice at a time. So if let's say I take this slice, right, and if I take this slice, it's a metal oxide semiconductor, and this is ground, and this is VG, right? If I take this slice here, slice at the very end of the drain and do the same thing, so it's still going to look like metal oxide semiconductor, but now this is VD, right? So which means that and you remember the charge density, and let's say both VG with respect to ground and VD are greater than VT, right? So let's assume that. Then you know that this charge and this charge which is formed here, this charge is Cox times Vg minus Vt, right? This charge accumulated here is Cox times Vd minus Vt, right? Now, which charge is greater, this or this? Because Vg is greater than Vd, right? Which means that this charge is greater than this charge, which means that this charge. So that's why you see it's shown as a height, but this is just for visual, basically. There is no height. There's still a very thin sheet of charge, but the charge concentration is different. So that's shown with this height, basically. So it's a visual thing. So you can see that this charge at this very end is higher than this charge here. And obviously it's kind of linearly goes here because the voltage is kind of linearly changing across this. So here the charge is lower than density than this node, but higher than this node. This charge density is higher than this here, but lower than this, and so on. Okay, so your charge density is actually varying across the channel, and I've written that as a one equation where it is Cox times VGS minus VCY minus VT, and this VCY is the channel voltage with respect to ground as you're moving along, right? So VC is equal to 0 at this end. So you can see Y is equal to 0. So VC at this end, VC at this end is equal to 0, and VC at this end is equal to VD, right? So your voltage is varying between 0, VC is varying between VT to 0, and as it is varying, you can see this is minus, which means that your charge density is also varying by that amount. Okay, everyone clear about this one? It's pretty important because that's where your saturation current and everything comes into picture, and that's
Sir, I
how.
have a doubt.
Yeah, go ahead.
Sir, in a like in a metal
Yeah,
sheet, how is this possible to have different potential at different places?
it is not yeah, great question. It is not a metal, it's a resistor. Okay.
Sir, like the gate I am talking about.
The gate is same voltage. The gate is also a resistor, but gate doesn't have different voltages. Why are you saying gate doesn't have different voltage? Gate is just one constant voltage. So this is VG, So everything is VG, 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 VG. The drain has a different voltage. The source has a different voltage. This source end, which is connected to this end of the channel here, is 0 volt. This drain voltage is connected to this end that has VD with respect to ground, but VG is constant throughout.
So
But I,
basically, you are taking that voltage difference.
oh, I'm sorry, you're right. I think I made a mistake here. Yes, yes, you're right. This is VG, not VD. What I wanted to show here is that uh, this is VG minus VD minus VT is what I wanted to show. Okay. Okay. Makes sense?
Yes, sir.
Yeah. Sorry. Good catch. The gate terminal is always VG, but the difference between at the oxide is VG minus VD in one case and VG minus V0. So basically this end I have shown here, this end. So let me redraw this here. I mean, redraw this here. So if I take this, so this is obviously ground, but you have a channel now, right? So this channel voltage here, that is also ground. This is VG, right? So then the charge accumulation here is Cox is equal to Cox Vg minus 0, because it's the difference between these 2 points here. Minus 0 minus Vt is your total charge. Q at the source end, let's say. QSS, let's say. QS at the source end. Okay, and now if I redraw this over here, so you have this block now, and you have this metal oxide. So this is silicon, this is oxide, this is poly, and so this is still VG, right? And you have a channel here now, but this channel end is connected to the drain side, right? And the drain voltage is VD with respect to ground, obviously. So that means this end here is also VD. So which means that the charge here is QSD, let's say, is C. I write it somewhere again. So the charge here is, I'll call it QSD, is equal to Cox times Vg minus Vd minus Vt is the total charge. Okay, so that's why this end, your charge density is higher because it's Vg minus Vt. So let's take an example. So let's say Vg was 2 volts and Vt was 0.5 volts. So here it will be Cox times 2 minus 0.5, right? So it'll be Cox, so the charge will be 1.5 times Cox here. And let's say Vd was 1 volt, then this would be Cox times 2 minus 1 minus 0.5. So this will be 0.5 Cox. So it's almost 50% or 2x, 3x lower basically on the charge density on the side. Makes sense? So good catch. I think I drew that by mistake. The gate voltage is not varying. The gate voltage is constant. It's like a metal, right? So it's constant. But I thought what the question you're asking is that if the channel is looking like a metal sheet, then how come there is voltage change? But yeah, the channel is a metal sheet, but it's even a metal is a resistor. It's just a low value resistor, but it is a resistor, and there's a current flowing through it. That's why you have that change. Whereas on the gate side, you don't have any current flowing through it, so it's just same throughout, right? Okay, is that clear, everyone, or any questions? And here you see the title of the slide, which says Gradual Channel Approximation. And the reason it's called Gradual Channel Approximation is, I assume that, I'm calculating the charge where it is Cox minus, so I'm calculating this charge, Cox minus VGS minus the channel voltage at position Y minus VT0. So basically I'm assuming that VT is same throughout the channel, but in reality it is not. So that's what it's called, gradual channel approximation. But this is, like, as I said, it's what's called the level 1 model. And for level 1, this is usually pretty good. 1 second, looks, I always have trouble seeing the chat window. I don't know why this is happening. This, okay. Okay, so you're just saying, sorry, I need to. Okay, so clear so far? Okay, so now that you are hopefully convinced that once I apply a VDS which is significantly larger than what we did before, then you're going to have a channel charge which is going to vary, start with a higher density and slowly going to vary till the drain node, right? And so what I'm going to do now is what I've shown here is I have taken basically taken just that channel which is formed, the inversion layer, and I'm just showing you as a kind of a three-dimensional structure to derive that IDVDS equation. And like I said, the height is showing you as the charge density. In reality, there is no height. I mean, it's still a sheet charge, just to show you visually. So, and you can split this just like we did for the, when we derived the equation for our block of homogeneous resistance, and that resistance was homogeneous in the sense it was even, right, from source to end. But now, because the channel charge is varying, if you represent it as a resistance per unit length, the resistance is going to be different. It is going to start with a smaller resistance at the source end here, for example, source end here, and it's going to get bigger and bigger, and at the drain end, the slice, if I take a slice here, the resistance is going to look larger. So basically for same unit slice like I've shown here. So if I take a unit slice here and find the resistance of this little thin block, that's what I'm showing as a series. Okay, and obviously the IDS flowing through is same because it has to obey KCL. And if I want to find out the incremental resistance for this one, I'm going to use my previous equation which we derived already. So it's going to be that length of that incremental length here divided by the W times the mu n times the charge density at that point, right? This is a differential equation right now. So at that point. And this charge, we said it's going to be Cox times Vgs minus the channel voltage at that point minus the threshold voltage. I should write Vt0 here. And if I know the dr, then the voltage across this tiny resistance here is the IDS which I'm trying to find times this dr. So I write this equation in this form, and then I integrate it from because it's a differential equation now and it is not constant, so I need to integrate it from 0 to L. So this is 0 to the length of the device, and for the voltage I integrate from 0 to VDS, because this voltage is varying from this VC of Y is varying from 0 to VDS. So I integrate from 0 to VDS, and that gives me my second set of equation, which is IDS is equal to mu n Cox over 2 divided times W over L. So proportional to W. If your W increases, current increases. L increases, current decreases. Makes sense. Same reason as because of resistance, because that's really what it is. It's a resistance here, voltage controlled resistance here. And then it obviously is dependent on the gate voltage as well as the drain voltage, because um, in the last case we saw, because it's a resistor here, right? So if you change the drain voltage, it will drain. But now we have this VDS square term, which we didn't have because we linearized it last time. So you can see that the previous equation I derived, I can get it from here too. And this is, I keep saying, as an engineer, you have to keep always doing sanity checks, because just to make sure, they all match. So if I take this equation and apply the same condition I did for the previous one, which was I said VDS is very small. If VDS is very small, then the square term will be negligible. If you remove this, then this 2 and 2 will cancel, and then I get the previous equation, which is mu n C ox W over L VGS minus VT times VDS, which is a linear equation, right? Now you see it's called linear mode. That doesn't mean this equation is linear. It just means that you know, the current is varying with the drain source voltage. It's not constant, because when we talk about saturation mode, that's why this is called linear mode. But in reality, it's linear only for small amount or small VDS voltage. Otherwise, it's obviously square, which is a nonlinear equation. Oh. Okay, as current is not flowing in the gate, how the voltage of the gate terminal is decreasing continuously towards the... Yes, so Sandhyanani, that was a mistake, what I was drawing. So the gate voltage is not changing from gate to drain source. You're right, because there is no current flowing, the gate side of it is constant. The drain source side, the channel side is the where your voltage is varying. Okay. Hope that answered your question. All right, so now if you, so like as I said, so let me go back here. Let me go back to one slide before. Now, if you see how I was explaining, right? So you can see at this end, this channel charge is equal to Vg minus Vt. And at this end here, this channel is equal to Vg minus Vt, right? Now, you'll see that this is, as Vd is increasing, this channel charge is decreasing. Now, once this Vd gets to the point where it is equal to Vg minus Vt, okay, or in other words, I can say, since everything is referred to source node, so if this, let me write this here, if this equation, in this equation here, Vd is equal to Vg minus Vt, or since everything is referred to the source node, I can write this as Vds is equal to Vgs minus Vt, right? Then this channel charge QSD becomes 0. Okay, so this channel charge here becomes 0. So, and this is what's called the pinch-off region. So that's the third region of operation. I mean, in typical books, this is second region of operation. I divide them into this, you know, sort of the linear mode, nonlinear, and saturation mode. So you can see as you keep increasing, this is not right. Yeah, there should be a drain voltage here, obviously. So this drain source voltage, when it gets to VGS minus VT, or I should say greater than equal to VGS minus VT, then this will pinch off. Now, if you take the previous equation, you know, which if I write it here, let me write it here. So in the previous equation, IDS was equal to mu n Cox over 2 times W over L, 2 times VGS minus VT 0 or VT times VDS minus VDS square. Here, and then once you reach that top point, can you guys hear me properly? I see some disconnection here. some of you say yes if you can. Are you able to hear me properly?
Yes, sir. Yes, sir.
Okay, good. Yeah, I saw internet connection broken, so just wanted to make sure. Okay, so so if you plot this equation just as a mathematical equation without knowing what's going on inside, you're going to get this parabola, right? Because you have this VDS squared term. Now, this part of the curve here is actually non-physical, because what it is saying is that you have this negative charges here. Once you reach that maximum point, then positive charge starts building up to cancel this and reduces this current. But that's not possible here. I mean, you have positive carriers, but as long as there is um, the negative carriers here, you can't have this cancellation. This is just not possible. So, but if you look at it physically, you will see what happens is, so you get a, so if I just sort of exaggerate this here, so you get this channel, right? And it kind of pinches off. And so you have this source side, which is ground. And then you have this drain side, which is your drain voltage. And this VDS is now greater than VGS minus VT. So you get this, I have exaggerated it, but you get this region where it says the channel charge is not there. Now, the first thing people assume is that, oh, if there is no channel charge, the conduction is going to stop. Now, that's a sort of a valid, kind of intuitive, but it is wrong in the sense because this cannot look as a dielectric, right? Because you have a varying channel charge. If you have a varying channel charge, you got to have electric field. There is motion of charge here. If there was no motion of charge here, then it would be flat. And if there is a motion of charge, then what happens is this is actually not very far. And essentially what you have is you have a depleted area and you have mobile charges, and you have a high electric field. So it just punches through. I mean, punches through in the sense it doesn't destroy it, but it just travels through. Okay. So you have current flowing it, you have charge, and you have a depletion area. It doesn't stop you from flowing because there is an electric field which will just push it through. If this distance was really, really large, then you would have recombination and all that, but this distance is small for it to just punch through. And now, because this is almost not changing or changes very, small compared to the channel length for a long channel approximation, you can assume that this current is almost constant now after it reaches the point. We'll see, we'll get to the next set of equations, which is not true, but just assume that now you've reached this point and this length is not changing much, and the charge density is obviously same as before here. Here it is 0 and this length is not changing, which means that this gradient is also the same. So your current almost becomes constant after this. Okay, so instead of going to 0, it falls constant. So which means that I cannot use this equation in this region here anymore. So I have to, but I can sort of derive it from this equation because if, one second. Yeah, so what I'm saying is that you've reached this point here, and after that, this equation still needs to be continuous. You can't go like jump like this and go like that, right? It needs to go continuous, and it needs to be constant, and that I can get from this equation. So if I make VDS is equal to VGS minus VT. So basically what I'm saying is that this equation is no more dependent on VDS, but I want to find out what that current is. And I say, oh, that current is the current at the VDS value equals to VGS VT. Plug that in over here, and that becomes your current from here onwards. So in other words, if I take IDS is equal to constant for VDS equals to VGS VT, then I plug. So what I'm showing here is I take the IDS linear equation and plug VDS equals to VGS minus VT because I want to remove VDS term. And then it turns out to be this equation. If I solve it, then it becomes VGS minus VT square. So you can see now that the drain to source current does not depend on the drain to source voltage anymore, because we kind of forced it to look like that because we know that it is almost constant. And we also know that at the time when the channel, what's called pinch off region, at the time it pinches off, this is the value of the current, right? This is the value of the current at the time when it is pinching off, which is the value of VDS is equal to VDS minus VGS minus VT. Okay. and and I say, okay, it remains constant from here now on to this, and it doesn't remain constant. We'll adjust that too, but for now assume that it's almost constant. Okay. And this is a very important, in analog or digital design, this is important. We call this VGS minus VT. There are a lot of terms. We call it V on, we call it VD sat, we call it V excess. There are different names, but they all means this excess voltage over here. Okay. So so essentially all the text you'll see, it's two regions of operations. One is the linear operation and one is saturation, what you saw. But I showed you that you can take the linear region and even approximate it for smaller VDS and show that it is like really linear for small VDSs. Okay. Any questions on the saturation mode equation? And we'll summarize this soon after. Everyone clear about the equation so far? This whole pinch off region is, it's very counterintuitive. You just kind of sometimes you have to just take it for granted because, the way I explained it, there's a lot of holes in it. So if you start kind of questioning it, then, it becomes difficult. So that's why you just have to level one. It's like, it's like band diagrams, right? Band diagrams are a statistical approximation of the quantum mechanics of the atomic structure, but it's a really good explanation. But then you start asking a lot of questions, then at some point it'll fall apart. Same thing with these, but they are pretty good approximation just to give you, first order tools for you to do design, basically. Okay, so now I'm going to just going to summarize those three equations. So what we are looking at is this is drain current, so we call it IDS. This is your drain voltage, VDS, and it's a family of curves because I'm changing VGS as well. So you can see here, so VGS, I've already written here. So VGS3, VGS3 is greater than VGS2 and VGS1. That makes sense because as your gate voltage is increasing, channel charge is increasing, and that's what is increasing your drain current as well. So this direction is VDS same and VGS increasing. So that's your square law. In this region over here, so if you take a constant VGS, you'll see that it has this sort of nonlinear dependency on VDS till you get to this point where VDS is equal to VGS minus VT, and after that it's almost constant. And if you go to the regions where VGS is really small, it's pretty much linear. So it's a linear relation between IDS and VDS where this it's kind of voltage control linear resistor, like what I've shown here, which is this value here. And like as I was saying, in analog design, we actually use this region quite a bit. Now, if you go to the region where VGS is greater than VT, channel is still formed, but VDS is less than VGS minus VT, which is the case here also. But now you're going from a small value to less than VGS minus VT value. Then it's given by this quadratic equation, which we just derived. Now, if it VGS is greater than VT, but VDS is greater than your saturation voltage, drain voltage, then it's a constant current which is given by this. And like I was saying, you can get this equation by plugging in VDS equals to VGS minus VT, right? Over here. So that's how we got the equation. Okay, now we're going to add, this is really not constant, so I'll sort of show you a reasoning behind it, and then we'll add a term to the equation to finally kind of complete the IV characteristics. So, like as I said, when you pinch off the channel, and it's kind of exaggerated here, it's kind of exaggerated here. So when you pinch off the channel, the real channel length is the channel length of your charge, which is, I'm calling it L dash here. And because you have this region of no charge, so we'll call this delta L. So your real effective L is less than the drawn transistor L by this delta L term, right? So, and when you're increasing the VG after increasing VD after VGS, what happens is this length slowly decreases, and it is not a linear relation. It is I mean, it is a linear relation, but the way to derive it is, it's a little bit complicated. So people just use the empirical data, and I'll show you that empirical constant. Okay. So basically, in our gradual channel approximation, what we had done was we said we took a slice here, dy, and we found out what the slice charge density was. That was Cox times VGS minus VC of at y minus VT, and we integrated from 0 to L, 0 to VDS, right? But now we're going to add the term we're going to make a modification, knowing that we don't integrate it to L, but till L dash. Okay, so I'm going to take this L, instead of integrating to L dash and to L, I'll integrate to this point L dash here, and then the VDS, I'm, instead of integrating it to VDS, I know that it's a constant term now, it's not changing, so it's VD sat, which is VGS minus VT. Okay, I do these two modifications, and then what I get is this equation here, mu and Cox, but now instead of W over L, it's W over L dash, which is smaller than the drawn length. If it is smaller than the drawn length, then the current is larger than what it was at the point of pinch off, right? And if I write this L as L dash is equal to L minus delta L, and this delta L is proportional to VDS minus VD sat, and we know that empirically. And I mean, from physics also you can find out, but like as I said, it is a little bit more complicated. So I can write this L dash as L times 1 minus delta L over L. I'm doing this because I know that delta L over L is a small term, so I can do just a sort of a Taylor expansion, take the linear term. And empirically, this term over here is 1 minus lambda VDS. So this delta L over L is directly proportional to, delta L over L is proportional to VDS, and that constant is lambda. Okay, so and if I basically this is in the numerator, and like I said, since I know lambda VDS is much smaller than 1, or lambda VDS is 1 over 1 minus lambda, I can do a Taylor or binomial expansion of it and say the approximate one is 1 minus of minus lambda VDS, which is 1 plus lambda VDS, right? So now the correction term is mu n Cox times W over L VGS minus VT square, which is true till you, if you take VDS is equal to 0, like, or lambda equals to 0, then that's our old value. Now there is a lambda term, which is it's a smaller term, depending on how long or short or what type of device it is. And this term now tells you that the current is going to increase actually linearly with VDS by this term over here. Now for short channels, this is actually not linear, and there is a lot of vertical field effect and all that. So you do a lot of correction to this for short channels, and maybe we'll, when we do that lecture on talking about the different short channel and thin oxide effects will cover this, but for long channel you can approximate this, and for hand calculation and doing design, this is usually pretty good. And like I said, in analog design, even in a lower node, we use longer channels most of the time, so these equations are pretty much always valid. So if I make that correction to the summary I showed last time, now instead of remaining constant, it's going to linearly slowly increase with VDS, and that term is what we did the adjustment here, and sort of give you an intuitive reason on why it's changing. Okay, any questions so far? Okay, so can you please repeat what is lambda? So lambda is the correction term. So if you look at this equation here, like as I said, the physical derivation for lambda is a little bit complicated. So what people do is they do empirically measure it, and they basically just adjust it. And I kind of showed some physical meaning to it. And I kind of said, actually your effective length is decreasing. Because of that, your equation is really W by L dash instead of L. And this L dash is L minus this delta L here. And I wrote that in this sort of, kind of a Taylor series form. And what I said is empirically, this is derived as 1 minus lambda. I mean, this delta L over L is lambda times VDS, or linear function of VDS. And you use that, and you basically take it to the denominator, assuming lambda VDS is much less than 1, which is generally true. And then you get this as your approximate equation. And I'm showing in this graph that basically our assumption that this was exactly constant is no more true, but it is linearly increasing with VDS by this term lambda. So that's your lambda. So what is lambda? Lambda is the slope of this. So if you take this slope of this curve here and the saturation region, the slope is lambda. Okay, hope that answers your question. Yeah, for some reason I'm not able to see. Okay, now I can see. Will the graph of IDS and VDS not be downward parabola as there is minimum VDS squared term in the equation? Well, that's what I explained, right? Physically, it is not possible. So that's why we said physically why it is going to be constant, and then we said, okay, it's not exactly constant, but it's going to vary slowly, and that term that varying slowly, I said it is an empirical term which is adjusted, and that empirical term is that slope lambda. So basically, people who are familiar with BJT, you remember early voltage, right? So it's basically your early voltage. In BJTs, you remember you extrapolated this, you extrapolated this where it met the axis here, and you call this early voltage. So that's basically your early voltage in CMOS. But we always talk it as output impedance. Basically, what is the rate of change of output current with voltage, output voltage? That's your output impedance. But it's what's called small signal impedance, which I'll not go into here. It's a kind of analog topic. Okay, any more questions? Hopefully that's all clear. Okay, no more questions. Hopefully this is all clear to everyone, at least most of it. And you just have to go back and look at the the review material, and oh, actually, before I forget, maybe I should show you that. So if you go to our GitHub site, the course site, the course GitHub site, Yeah. So I added this section called session activities. So by date, I put the topic and link to the YouTube video which Santanu has been posting. So that way, at one place you can access it. So when Santanu gives you the link, I'll also put it up here. And I also gave you some suggested readings, like you can see for Vilisa Design, I give you chapter 1 and 2 for Hodges. Same thing for CMOS processing, suggested problems. So these are the exercise problems you should do. These are like minimum, at least you should do this to get acquainted with the material. And, and we'll do some assessment on the e-learning side as well. So I'll try to keep the e-learning side just kind of a minimal assessment, and more lengthier problems I'll keep it here for self-assessment. So this you just do it on your own, and we'll probably not assess it. If you have any fundamental doubts, you can ask that. But so definitely, every day take a look at it, and I'll go back and add some problems and reading sections and all that. So a lot of times I don't get time to update it right away. So keep looking at this. So make sure at least you read through the reading sections, and obviously you do it on your own. So now I've given you all the 6 textbooks. Download and keep it for your reference, and it'll be helpful for you. I added this little useful design parameters. This is the last page of the Hodges book actually. So this has all, a lot of the technology parameters for standard 0.18, 0.13, and resistivity and capacitances, and constants is physical constant. So this is a good one to have reference. So I added that one on the resources page as well. Okay, so just wanted to show this. So definitely take a look at this page every day to make sure, if you want to access the videos, problems, reading assignments, and announcements, and all that will be here. Okay. All right. So the last equation I wanted to show you is the IDS as a function of VGS, which is basically this question. So, but IDS as function of VGS, if you keep the VDS constant, then the region of operation is not known. So you have to make sure that the region of operation is either in saturation or linear, and this equation will change. But I've shown you one particular way. Like for example, if you connect it in this fashion, since VDS is equal to VGS, which means that VDS will always be greater than VGS minus VT, which means it will always be in saturation region. So if you vary the voltage, you can see it's a square law. And this is what gives you basically the amplification. And if you remember in BJT, this was exponential, right? So that's why BJTs are still used for, like as I was saying, if you need high-speed devices or large current devices for a given area, BJTs are still preferred. Good BJTs. I mean, you get a lot of parasitic BJTs from CMOS, but good BJTs, you need this. Okay, before I go on to the next one, maybe we'll take a short break. Let me pause the recording here. Okay, so yeah, just quickly repeat. So this is a typical layout of Nmos where you draw so actually here it is overlapped, but typically when you draw, this is actually one. So it's not like, let me show it in another color here. So this is actually one rectangle. It's not maybe deceiving that you're drawing one source and one drain area. No, you draw one and overlap this gate on top of it. So when, as I was showing yesterday, when the foundry house takes it, they will have the diffusion mask, which will be a complete mask, and they'll do all the implant and everything using this mask basically. And then on top of this, you put the gate. Okay, and the overlaps and all that we'll talk in detail when we're talking about layout. This is Pmos. So in Pmos, obviously, you can't put the P plus in the P substrate because that will create a short, obviously. So first you have to create a N-type well, which is called an N well, and then you do your P plus. I mean, you put your gate, then do the P plus implant. So that's again the same thing, source and drain here. So in Pmos, the whatever is your positive side, that's your source. I mean, sorry, that's your uh, yeah, that's your source and this is your drain. That's because in positive, this is majority carrier is whole, so that's the source of your carriers. But again, same thing. I can make, if I apply a positive value here compared to here, this becomes your source, this is your drain. If this is positive with respect to this node, then this becomes source and this becomes drain. So it's a symmetric device. Just be clear about it. Okay, so just to capture all the summary of all the equations we have derived so far. So the first condition is if Vgs is less than Vt, then Id is equal to 0, which is not true. There is a small amount of current and what is called a subthreshold region. But for a digital, when you're trying to do high current switching, then this is a pretty good approximation. In fact, in analog design, we do use the subthreshold region of operation very extensively, especially in low power applications. The linear mode, which is this equation here, which is a square law. So you have this beta term times the geometry, which is W over L, then 2 times the excess voltage, VGS minus VT, times the drain to source voltage minus VDS square. This is for the condition where VGS is greater than VT, so that you can form the channel, and VDS is less than VGS minus VT, so the channel is not pinched off yet at the drain end. And if you take this equation and make the VDS really small, then you can neglect this term, and we showed this from the derivation of the channel as well, that it turns into this sort of this linear equation. So it's a linear relationship between ID and VDS with this sort of resistive term, which is controlled by the gate source voltage. For a constant gate voltage, gate to source voltage, it's linear as long as the VDS is very small. I mean, approximately linear. How linear depends on how linear you want it. If you want 0.1% linearity, 0.01% linearity, your VDS has to be really, really small. And then we made the adjustment, and then the saturation mode is after when VGS is greater than VT and VDS is now greater than VGS minus VT. If that's the case, then you get a constant current term, and then you have this adjustment because your output current is actually a function of VDS, but it is a kind of weak function, and this is a function of your technology as well as your length. If your length of your device is larger, so lambda, this term lambda is directly proportional to 1 over length. So if your length is larger, this is smaller, which means that it'll be more close to a constant current rather than a varying current with respect to VDS. So like, for example, in analog circuits, a lot of places, amplifiers, current sources and all that, we want this lambda to be really small, like 0.01 or 0.01. This, then we just have to increase this length to whatever it is needs to be. And for the PMOS, maybe I just wanted to highlight this. For NMOS, obviously this mobility is the mobility of N-type. COX is same for both because the same thin oxide. For PMOS, it's the same equation. Obviously, your mobility becomes mu P, and but the signs, they change. You can see now VGS needs to be greater than VT. So if you have a PMOS and this is your source node, this is your drain node, and then you apply a gate to source So you can see the gate to source volt is a negative voltage now, or in other words, okay, so I think I didn't write this correctly. Yeah, so this one should be less than. Yeah, should be less than VT, because VT is actually a negative number. It's a negative number. VTP is a negative number. So when VGS is less than, that means you're basically, this voltage is larger than the mod of VT. Okay, so essentially all the signs changes. So you can see now VGS should be less than VT, and VDS should be greater than VGS minus VT for linear mode. And VGS should be less than VT and VDS small. You go back to that linear equation. And for saturation region, VDS is less than VGS minus VT. VGS is less than VT to give you this equation. Now, when I started designing, this negative sign used to confuse me a lot. So I used to just take mods, right? So you can take VGS mod greater than VT mod. And same thing over here. Same thing over here. VDS is greater than, less than mod of VGS minus VT. Okay. And if you do that, then you can just assume it as those your Nmos equations. But you have to make sure you're biasing it properly. You can't, like, you put the mod, but you bias this like that, then obviously that'll be wrong. Just quick on the symbols. So you'll see that in digital Nmoses are just 3-terminal devices like this, and in the Pmos is with a bubble here, and bubble basically kind of shows you as an inversion of Nmos. In analog, it is kind of overwritten here. In analog, the Nmos is shown with the arrow, and essentially it's showing you that this, if it was the drain and that's the source, then the current will flow in this direction. So that's the direction. But like I said, you'll get a schematic symbol like this, but that doesn't mean that you can't rotate it. But you just don't want to rotate it to avoid confusion, but you don't want to avoid. And the PMOS is shown with the arrow inwards, because then the same thing. Your drain and source is biased like this, where the source end is this, and the current flow will be in this direction. So it's showing the flow of the current basically. So these are two typical symbols. The other ones, don't worry about it. So regions of operation, like as I said, the linear region is where your channel is completely on till the end. It's a gradually changing channel, but it is still there. During the pinch off, at the point where it is being pinched off, this channel just pinches off right here. And then as you keep increasing the VDS, this sort of pinch off region starts expanding. Obviously, it's exaggerated here. It's a lot smaller than this. Okay. Okay, I think that's all I have for the regions of operation. So the next we are going to look at capacitances. Any questions before I go into talk about MOS capacitance? Any questions on the region of operation, or current equations or MOS capacitance? Okay, so hopefully you guys are following it. And like I said, go through the reading assignments, the problem assignments, and that's the only way to do it. But if you are absolutely not clear about something, you should ask now. We have plenty of time. Don't worry about time. Okay, so now I'm going to show you what are the different intrinsic and extrinsic capacitances which are part of the MOS device. So let me just give me a second. Okay, so so I'm going to talk about the different capacitances in a MOS device. I think by now you probably seen the biggest part of the capacitance, which is the gate to substrate or the gate to source part of it. But there are other sort of parasitic capacitances which are also associated with the device, which which plays a big role, especially when you're looking at high performance, high speed circuits. Okay. So here I've shown you the layout and the cross section. You can see that so this is the layout. So that's your gate area, and this is your yeah. So this is your gate area, and that's your source and drain area. Now you can see what is shown here is you remember when we were talking about processing day before yesterday. You do diffusion, right? Or you do ion implantation and annealing. In both cases, they kind of like diffuse into the substrate. But when they go downwards, like when the diffusion is going in this direction, they also go sidewards, right? So because of that, these source and drains, they kind of extend into your gate area, a little bit into the area, which is actually fine. The other way is not fine. If you have the extension where you have a gap, then the device is going to be completely off. If you have an extension inside, that's fine. Just that now your length, so in your layout, you drew the length as LM, like I've shown you a drawn length. But because you have this extension, which I've shown as LD, which is the L diffusion, so because it is diffused, so now your actual length is whatever you drew 2 times that drawn length. And these are all part of the model, actually. They are not part of layout extraction, because they know that this actually happens in the layout. Now, there are variabilities between different times. So the process can go through different times where the LD is varying over a range. And that's what, when we start doing the corner simulations, you'll see we will talk about process corners. So that's what the process corners are about. They'll give you a range. They'll say this LD is going to vary. I mean, it'll be part of the model. So when you take what's called a slow process corner model, then this LD could be like, let's say 2 nanometer, right? And let's say you go to fast, and they'll say, okay, for this process corner, LD is going to be 1 nanometer, or whatever it is, right? So they give you these extremes. So when you simulate, they are part of the model, and we'll talk more about modeling tomorrow. And so that is embedded in. So this is this doesn't have to be part of the parasitic extraction. The parasitic extraction is to do everything which is beyond the normal device, basically drawn device. Okay. So in let me just erase this 1 second. So there are 2 types of capacitances in MOS devices. One is the oxide, which we have been seeing so far, when we did metal oxide semiconductor or metal oxide metal. So this capacitance is related directly to the thin oxide, which is grown below the poly, basically. But the other type of the cap is these diffusion caps, which is called junction capacitance. And if you remember yesterday when we did PN junction, we applied a reverse bias. And these are all reverse bias, because typically this node is all ground, because that's substrate. For an NMOS, for a PMOS, it'll be the opposite. The P type will be the source, and drain, and the the n-type, yeah, the p-type will be the source and drain, the n-type will be the n-well, and the n-well will be VDD, so it'll still be reverse bias. So you saw that these when we apply a reverse bias, sorry, positive voltage here and negative voltage here, this actually looks like a nonlinear capacitance, right? So you basically have these nonlinear capacitance CJs all around this, and these are obviously parasitic caps. The gate cap, you can kind of think that as a parasitic cap because all you're trying to do is control the channel, but because of that you also get a oxide capacitance, and the source and drain are also parasitic caps. And you see that because of these overlap regions, so there is a tiny amount of oxide cap between the gate and straight to the source and drain. So you have these tiny caps, they're called C overlap caps. So you have those caps. So now if I draw the schematic of a 4-terminal device and show you physically how each cap is translating to. Okay. So the first cap is the gate to source cap. So the gate to source cap is the gate to source node, but when your channel is on, the channel is completely on, and I'll show that in another slide just in a few minutes. So this is actually a bias dependent one, and I'll show you why it's bias dependent. Because when a channel is formed, this gate to this channel is the total cap, but because your node is divided into 2 nodes here, so let's say the channel is completely formed, right? So you have this is your source, this is your drain, and you have this channel completely formed here, right? And you have this gate here. So let's say the VDS was 0, almost 0. That means you'll have a uniform channel here if VGS is greater than VT. Then this oxide cap is between the entire gate and this thing. But we don't have this node in the schematic, this channel. We don't have access to this node, right? We have access to the source, we have access to the drain, and we have access to the bulk. So that's why we have to split this. And so that's why you'll see CGS is split into half when the channel is formed completely in linear mode. And the other part is shown in gate to drain mode, gate to drain capacitance. So that's, if you look at the layout, you're showing half of it is over here. And I'll show you that this is actually bias dependent. And then CGD is the other half, right? So this is the other half. So this is the other half which you're showing as CGD. Okay. And then source to bulk. Okay, the source to bulk is this diode capacitance here. And that's what you saw. So this is, so I've shown this in, excuse me. So I've shown this green to just show you that that's the oxide cap. The red ones are in the junction caps. The red ones are oxide capacitances. And similarly, you'll have drain to bulk, which is this diode here. And these are nonlinear capacitance, depends on the voltage from drain to source and source to drain, basically. Okay. So like I was saying, these caps, especially the gate to source, gate to drain, gate to bulk caps, these are bias dependent caps. So for example, when you have the in the cutoff region, when there is no channel formed at all, then this between the gate and source is only this tiny overlap cap, right? Because you have this tiny overlap cap, because now the channel is not formed. So which means that this cap now is in series with this depletion diode here, and then it connects to the substrate. So like as I was showing when we started the class, I was doing some problems. So basically this cap, the gate to bulk cap is 2 caps, and this is C ox, and this is, let's say, C depletion, the depletion cap or the junction cap. And that's this cap. And then on the drain side, same thing. The cap is only this overlap cap, because now the channel is not formed, so you don't see any of these fields get terminated to the drain side. You don't get any of these fields get terminated to the source side. They all get terminated in the substrate, and you have a substrate connection. So you're going to see a substrate Okay, so that's what I'm showing during the cutoff. So when VGS is less than VT, so cutoff, if you remember, VGS is less than VT, then if I look at the cap from gate to drain and gate to source, it's just this tiny overlap cap. And then drain to bulk and drain to source, I still have those diode junction caps, right? And then I've shown you, and a lot of times people miss this, you have a gate to bulk cap, but it is this gate, it's a series cap, which is the oxide in series with a diode, basically reverse bias diode. So that's your cutoff region. So here I'm showing different caps. I'm showing CGS, CGD, and CGB gate to bulk. And you can see, and for this graph, definitely refer to the Hodges book. Don't look at the Kang's books, because the Kang's book actually has an error in this one. I forget what the error is, but there is an error. So you can see the gate to bulk capacitance during the cutoff region. As your voltage is increasing, the capacitance is decreasing because this depletion region is increasing, right? So that's why you see the capacitance actually decreasing. And when the channel is turned on, the gate to bulk capacitance becomes 0, because now you have a plate underneath it, and you have a connection between here and here. There is no connection from bulk to gate. I mean, there is no charge flow from gate to bulk anymore. It's all between gate and source and gate and drain. Okay, so when you reach VT, the gate to bulk just kind of goes down to 0. So now if you look at the linear region, you have a complete channel formed, right? And like I said, your total cap is Cox times W times L, but that is between this and this gate and this channel. Between gate and channel, but I don't have access to the channel. I have access to the source node and I have access to the drain node. So in linear region, what they do is they split the cap. They split this cap. So half of Cox is in the source side, and you have the C overlap, and the other half is on the drain side, and plus this overlap. Okay. So if you look at CGS, then it is half of gate, which is half of Cox times W times L, and then plus the C overlap, which is always there, doesn't matter what the region of operation is. And then then you have the junction caps as well. So you can see now when you went from the VT to the linear region. Okay, so actually this is the region, because VGS less than VGS minus VT is this region. So we are talking about this region right now. So when you're in the deep linear region, your CGS and CGD are half. Then as you get close to saturation, I'll show you in the next slide, as it goes in saturation, so obviously you always have the overlap. But because you have this pinch-off region now, so the gate to source is 2/3 of CGS. Why is it 2/3 of CGS? It's a little bit complicated. So again, read the CVDS book. It talks about partition theorem and all that. But it's essentially 2/3 of Cox times W times L. Yes, this quantity here. And then you have the drain to bulk and the source to bulk. And gate to drain is just this overlap, because now there's no channel connecting here. So there is no field. The only fields which are going from gate to drain are these overlap area. After that, all the field is this channel area. And then you have some gate to source, but that's a tiny portion. Most of it is just gate to source. Okay, so that's the region of operation. Can you guys hear me? I think the connection is a little flaky now.
Yes, sir. It's okay.
Okay, good. Okay, so those are the different regions of operation. Different caps for different regions of operation. Any questions, on the caps? Why are they varying? So just to kind of reiterate, so if you look at this cap versus VGS bias dependent cap, the gate to bulk, that is this cap, starts with the entire Cox. So let me maybe write it here. So this is the complete cap CG, so which is Cox times W times L. So it starts here and then goes down to 0. When the channel turns on, there is no cap from gate to bulk anymore. The CGS, gate to source cap, doesn't start till a channel is formed. And when you're in deep saturation, it is 2/3 of CGX, or 2 times 3 times Cox times W times L. Okay. And the gate to drain is basically 0. And in linear, it is basically both of them are equal, which is half times Cox times W times L. Okay. This is the oxide. And plus, obviously, you have the overlap capacitances. So all the overlap capacitance is always there. And then drain to bulk and drain to source always remains. That's the junction cap, which is always there. This is only the oxide cap, which is varying. Okay, so this is just showing you the different caps. So CGS in accumulation mode. So I didn't talk about accumulation mode, but when you go negative, your gate value is negative compared to the source. Because you have a p-type material, positive holes actually gets accumulated on the sheet, and so you actually get a capacitance, but you don't get any conduction because your source and drain. So if I draw it here, so you have N plus, you have N plus. This is a p-type material, and you have a gate, and so if you apply a negative voltage, right, you have a negative voltage with respect to bulk, then you get positive charges here. So it looks like just like Cox, right? Because these are mobile carrier, but you can't conduct any current through this because there's only majority carrier is negative here, right? If there were positive carriers, you could conduct it. So this is called the accumulation mode when VGS is less than 0. Basically, it's negative. So that's your accumulation mode. So your CGS still has, so the overlap cap is always there. And so in accumulation mode, it's C overlap. Depletion mode, it is C overlap. In saturation, it is C overlap plus 2/3 of Cox, and in linear, it's half of Cox, right? And then CGD is again C overlap, C overlap, C overlap. So it remains basically 0. Only in linear mode, it is C overlap plus half Cox. And then the drain to source and source to bulk, because they are diode caps, they're always there. So it's CJ all the time, but obviously depending on the voltages, they will vary because they're voltage dependent caps. Okay, any questions on these capacitances? What about fringe caps? Fringe cap is part of this. So when they calculate CG and all that, that is part of the fringe cap. So when I'm showing you Cox, I'm just showing you the parallel plate, but the fringe is also included in that. Because this is thin oxide, so fringe is actually a significant portion of it, but that's actually part of the model. So good question. That's part of the model. And that's not part of like post layout. In post layout, you have fringe cap of the vias. So I think when I was doing the thing, I think it was Sandhya who asked, like, what about the capacitance from the via to some node? And those are there, the small caps, but they will be captured as part of your post layout parasitic cap. Okay, any other question? Okay, so question from Srishti Rani is, why are we taking half Cox? Yeah, I mean, it's an approximation. The real models actually have actually even in the real model, because what it is like, as I said, so if you have the channel actually looks like a resistor, right? Like a small value resistor like this. So you have the source side, you have the drain side, right? So when the channel is completely formed and I want to represent the cap, right? That's the best I have, right? Because I can't put 2/3 and 1/3 here because that will be underestimation. Because it is resistive, so doing this half-half actually is very close. But if your operations are in like hundreds and hundreds of gigahertz, you have to use what's called non-quasi-static models, NQS models, because the one we use, what's called quasi-static model, this is resistance is actually 0. Okay, so the partitioning doesn't make much sense, or it might be off or whatever it is, but it's just it's the most convenient one for the modeling we are doing. right? Because in a real model, if you're using a non-quasi-static model, the channel and everything is represented properly. So there you don't have any issues. But if you don't have access to that, then obviously, then you're going to have to do approximation, and half Cox is kind of the best approximation. So you actually, again, follow the Resistivity book. They go through this partition theorem and tell you why values are. And like I said, these are level 1 model. When you go to level 2, 3, and model, and so on, they're actually kind of fudged. But the basic fact remains that you have access to the N terminal, so you have to approximate it. And for example, when you short drain and source, and I want to use it as a capacitor, then it works fine. It's only when you have, for example, you're doing an amplifier and it's in linear mode, and typically they're never in linear mode. If it is in linear mode, then it could be underestimation or overestimation, depending on how linear you are or how nonlinear you are. Those are the issues when you like really, really high speed. But the most of will be captured by the model, the way they partition it. Unless you are in the terahertz or hundreds of gigahertz range, then that's when you have to use what's called NQS model, which is typically never provided by the foundry house. They are very rarely provided by the foundry house. Okay, any other questions? Okay, so this is just everything I've already explained, just showing you a 3D picture of to give you a better idea of what the capacitances are. I think mostly I wanted to show you the junction capacitance. So if you look at the junction capacitance, the way the values are given in the model file, so you can imagine the junction as this sort of this square block. So if you look at, if you remember, we derived for the capacitance, we said Cj is equal to Cj naught, over 1 plus Vr over V. This Cj naught is actually different for the bottom part of this cube compared to the side wall. Okay, so in the model they'll actually give you two numbers, Cj naught and Cj SW. So I think I show you in the next one. So basically the way you calculate the total Cj is Cj naught times W times Y, which is this is W, and then whatever is the length of the diffusion, plus the perimeter of, and typically you take three sides of the perimeter, because on this side it's actually implant adjusted, so the diode cap is not there because you're just connecting it to the channel here. So like I said, but that's level 1. In level 2, 3 and all that, they actually take the doping profile and all that into account and do it. But essentially what you're doing is you're taking the bottom plate area, which is the area of the source or the drain, multiplying with the Cj naught value given to you by the foundry, and then they give you another number called CJSW, and then you multiply the perimeter. And this is all taken care of in the model itself. All you have to provide them is this parameters, and which is part of when you're doing schematic, you may not know your length and width. I mean, you know your width, but you don't know the length of the source, but it assumes that you're doing a standard layout. Once your layout is done, you do the extraction, then it captures the exact thing which is drawn, and then it calculates all these parameters out of it. Okay, so that's all I have. Any questions on these capacitors so far? Okay. All right. So we'll just stop here. It's time right now.